The laughter echoed through the corridors of the Reich Air Ministry on a cold Berlin morning in October 1939. Hermann Goering, resplendent in his sky blue uniform, had just finished reading the latest intelligence report on British aviation experiments. His voice dripped with theatrical contempt as he spoke to his gathered staff officers. "Gentlemen, the British are playing with toys. Gas turbines for aircraft propulsion? It is the fantasy of professors who have never felt the sting of combat wind across their faces." The assembled officers chuckled dutifully. Outside, the first snows were beginning to dust the streets of a capital drunk on early victories. Poland had fallen in 27 days. The Luftwaffe's Stukas had screamed down from clear skies. Why should the Reich concern itself with the desperate experiments of a nation already on its knees? But Goering was catastrophically wrong. While he dismissed jet engines as academic curiosities, British factories were already learning to breathe fire. By 1944, Allied production lines were completing 400 jet engines per month, while German factories struggled to build 80. Each Allied engine ran for 200 hours. German engines failed after 20. The mathematics were simple and unforgiving. Germany had invented the jet age through brilliance and daring, but the Allies were about to win it through discipline and manufacturing capacity. Each month of operations increased Allied numerical superiority, while German forces struggled to maintain minimum operational capability. This is the story of how industrial warfare silenced the laughter forever. How the nation that mocked jet engines as toys watched helplessly as those same toys, perfected in Allied factories, powered the final assault on the Reich. The laughter echoed through the corridors of the Reich Air Ministry on a cold Berlin morning in October 1939. Hermann Goering, resplendent in his sky blue uniform adorned with medals that caught the autumn light streaming through tall windows, had just finished reading the latest intelligence report on British aviation experiments. His thick fingers drummed against the mahogany table as he spoke to his gathered staff officers, his voice dripping with theatrical contempt. "Gentlemen," he declared, pausing to light his pipe with the deliberate ceremony he reserved for moments of supreme confidence, "the British are playing with toys. Gas turbines for aircraft propulsion? It is the fantasy of professors who have never felt the sting of combat wind across their faces." The assembled officers chuckled dutifully. Outside, the first snows of what would become the longest winter in memory were beginning to dust the streets of a capital drunk on early victories. Poland had fallen in 27 days. The Wehrmacht's panzer columns had carved through defences like a hot blade through butter. The Luftwaffe's Stukas had screamed down from clear skies, their sirens announcing the arrival of a new age of warfare. Why should aviation be any different? Why should the Reich concern itself with the desperate experiments of a nation already on its knees? But in that moment of supreme confidence, as tobacco smoke curled toward the ornate ceiling and the sound of jackboots clicked in distant hallways, the seeds of a catastrophic miscalculation were being planted. For while Goering dismissed jet engines as academic curiosities, the British were not building toys. They were building the future. And that future would consume his Air Force with a thoroughness that would have seemed impossible on that confident October morning. The reports scattered across Goering's desk told a story he chose not to read. British intelligence had been tracking German jet development since Hans von O'Hine's first successful test runs at Heinkel in 1937. They knew about the HES-3B engine. They knew about Ernst Haeckel's secret flights. They knew, with the cold precision that would characterize everything that followed, that Germany had achieved first flight of a jet-powered aircraft on August 27, 1939, just 4 days before the invasion of Poland. But knowing and understanding were different things entirely. The German leadership saw speed and declared victory. They saw a successful test flight and assumed dominance. They looked at their early lead in jet technology the way a sprinter might look at the first 50 meters of a marathon, with dangerous, premature confidence. The numbers that should have given them pause were buried in technical reports that never reached the upper echelons of command. The HES-3B engine that powered the Heinkel HE-178 on its historic first flight produced barely 1,100 pounds of thrust. It consumed fuel at a rate that would have emptied the tanks of a conventional fighter in mere minutes. Most critically, it had an operational lifespan measured not in hundreds of hours, but in tens of hours, sometimes less. Frank Whittle, working in a converted foundry in Rugby, England, understood these limitations with crystalline clarity. His notebooks from this period, preserved in the archives of the Royal Air Force Museum, reveal a man obsessed not with speed records or first flights, but with the grinding, unglamorous work of making jet engines that could survive contact with operational reality. Where the Germans celebrated their early achievement, Whittle catalogued failure modes. Where they trumpeted their technological superiority, he calculated fuel consumption rates and mean time between failures. The morning of April 12, 1937, had dawned grey and unremarkable over the English countryside. No fanners called attention to what was about to happen in the modest facility of Power Jets Limited. The air was thick with the smell of oil and hot metal, and the persistent vibration of experimental machinery had become so constant that the workers no longer noticed it. Whittle himself, thin and intense, his hands permanently stained with grease despite repeated washings, stood before his first operational jet engine like a priest before an altar. The engine was not beautiful. It squatted on its test stand like some mechanical toad, all pipes and awkward angles, its centrifugal compressor housing giving it a bulbous, ungainly appearance that bore no resemblance to the sleek projectiles that would eventually house its descendants. But when Whittle gave the signal and the starter motor whined to life, something fundamental shifted in the balance of global power. The engine spun up slowly at first, the centrifugal compressor drawing air through the intake with a sound like wind through a narrow canyon. As the RPM climbed, the pitch changed, rising from a low moan to something approaching a scream. Fuel flowed into the combustion chamber, and with a sudden whoosh that made every man present step backward, involuntarily, the turbine section caught fire with controlled fury. What happened next was not dramatic by the standards of later jet engines. The thrust produced was modest, barely 1,000 pounds. The fuel consumption was appalling, burning aviation gasoline at a rate that would have powered a conventional aircraft for hours in mere minutes. The engine ran hot, so hot that the turbine blades glowed cherry red within the housing, and the smell of overheating metal filled the workshop despite the roaring ventilation fans. But it ran. For 18 minutes, Frank Whittle's jet engine ran with steady, reliable power. No propeller turned, no pistons fired. Instead, pure thermodynamic force, the controlled explosion of expanding gases, pushed against the atmosphere itself. When Whittle finally shut down the engine, the silence that followed was profound. The men present understood, with the clarity that sometimes accompanies watershed moments, that they had just witnessed the death of the propeller age. The technical specifications that Whittle recorded in his log that evening would have seemed unimpressive to casual observers. The centrifugal compressor achieved a pressure ratio of approximately 4:1, modest by later standards, but revolutionary for its time. The combustion chamber operated at temperatures that pushed the metallurgy of the era to its absolute limits. Most significantly, the engine demonstrated the fundamental principle that would eventually power everything from fighter jets to commercial airliners, that you could create thrust by accelerating a mass of air rearward without the mechanical complexity of gears, camshafts, and spinning propellers. But while Whittle methodically documented every temperature reading and vibration measurement, the German jet program was making different calculations. Hans von Ohain, working under the patronage of Ernst Heinkel, had taken a fundamentally different approach to the same problem. Where Whittle had chosen the reliability of centrifugal compression, von Ohain had opted for the theoretical efficiency of axial flow. Where Whittle had focused on building engines that could survive extended operation, von Ohain had prioritized the demonstration of flight. The difference would prove decisive, though not in the way anyone expected. Von Ohain's axial flow design was, in many respects, more sophisticated than Whittle's centrifugal approach. Instead of using a single spinning disc to compress incoming air, the axial design employed multiple rows of rotating and stationary blades, each row adding incrementally to the pressure of the airflow. The result was an engine with a much smaller frontal area, better suited to installation in high-speed aircraft. In theory, it was superior in almost every measurable way. In practice, it was a mechanical nightmare. The tolerances required for axial flow compression were measured in thousandths of inches. The blade angles had to be precise to within fractions of a degree. Any distortion in the housing, any slight warping of the rotor assembly, any accumulation of dust or debris could cause the entire system to stall catastrophically. Where Whittle's centrifugal design was forgiving of imperfection, von Ohain's axial engine demanded precision that the German manufacturing base, for all its reputation, struggled to deliver consistently. The morning of August 27, 1939, should have been a moment of unqualified triumph for German aviation. The Heinkel HE-178, powered by von Ohain's HES-3B engine, lifted off from the runway at Rostock-Marienhohe with Erich Varsitz at the controls. For 6 minutes, the aircraft flew powered by pure jet propulsion, reaching speeds that no propeller-driven fighter could match. The flight was smooth, controlled, and historically significant. Germany had achieved the world's first jet-powered flight. But in the euphoria of that achievement, critical details were overlooked. The engine that powered the HE-178 on its historic flight was literally one of a kind. There was no second engine waiting in reserve. There was no production line capable of manufacturing identical units. There wasn't even a complete set of engineering drawings that would have allowed another team to recreate von Ohain's work from scratch. More critically, the flight had lasted only 6 minutes, because that was approximately the limit of the engine's operational endurance. The HES-3B was less a practical power plant than an incredibly sophisticated proof of concept, a demonstration that jet propulsion was possible, rather than evidence that it was ready for military application. Hermann Goering's reaction to reports of the successful flight encapsulated everything that would go wrong with German jet development over the next 6 years. He saw the speed, the dramatic visual impact of an aircraft flying without a propeller, and immediately began planning how to use this new weapon to terrorize enemy cities. What he did not see, what his staff did not emphasise, was that Germany had achieved a demonstration, not a capability. The British approach to the same problem was methodical to the point of being pedestrian. While German engineers celebrated their first flight, British engineers were focused on their 1,000th hour of engine operation. While German planners envisioned squadrons of jet fighters sweeping Allied aircraft from the skies, British planners were calculating spare parts requirements and maintenance schedules. The difference in philosophy was captured perfectly in a memo that crossed Winston Churchill's desk in the winter of 1940. Air Marshal Hugh Dowding, the architect of Britain's successful air defence during the Battle of Britain, had written with characteristic bluntness, "Speed without endurance is not an advantage, it is a handicap. An aircraft that can fly twice as fast, but only half as long, is not twice as effective, it is half as effective." This was not the kind of insight that made headlines or inspired dramatic speeches. It was the grinding logic of industrial warfare, the recognition that future conflicts would be won not by wonder weapons, but by the unglamorous mathematics of production, maintenance, and logistics. While Germany celebrated its technological achievement, Britain was already beginning the slow, methodical process of turning jet engines from laboratory curiosities into weapons of war. The contrast in metallurgy alone told the story. German jet engines of this period used exotic alloys that were difficult to manufacture and impossible to replace. British engines used steel. German engines achieved higher operating temperatures through advanced materials science. British engines achieved reliability through conservative design choices. German engines impressed test pilots with their performance. British engines impressed quartermasters with their serviceability. By the winter of 1940, as the Battle of Britain raged overhead and German bombers attempted to pound British industry into submission, the jet engine programs of both nations were moving in fundamentally different directions. Germany was refining its technology, pursuing ever higher performance from increasingly complex designs. Britain was industrializing its technology, sacrificing theoretical perfection for practical manufacturability. The numbers emerging from British test facilities during this period should have terrified German intelligence had they been able to obtain them. Whittle's latest engines were demonstrating operational lifespans measured in hundreds of hours rather than tens. Fuel consumption, while still higher than conventional piston engines, had dropped to levels that made extended combat operations theoretically possible. Most critically, the manufacturing techniques being developed at Rolls-Royce and other British firms were proving scalable. Where German jet engines required hand-fitting by master craftsmen, British engines were being designed for assembly by semi-skilled workers using standardized tools and processes. Where German engines demanded exotic materials available only in small quantities, British engines used materials that could be produced in tonnage lots. Where German engines were marvels of individual engineering achievement, British engines were being designed as components in an industrial system. The British had made a fundamental decision that would shape everything that followed. They had chosen to prioritise the reliable over the remarkable, the manufacturable over the magnificent. It was a choice that reflected not just different engineering philosophies, but different understandings of how industrial wars were won. As 1940 turned to 1941, the early German advantage in jet technology was beginning to erode through a process so gradual it was nearly invisible to contemporary observers. The gap in flight testing remained significant. Germany had operational jet aircraft while Britain was still conducting ground tests. But the gap in industrial capability was moving in the opposite direction, and industrial capability would prove to be the metric that mattered. The Allied recognition of the propeller ceiling came not from any single moment of revelation, but from the accumulated weight of engineering analysis and combat experience. By early 1941, both British and American aerodynamicists had reached the same disturbing conclusion. Conventional propeller-driven aircraft were approaching fundamental physical limits that no amount of horsepower or design refinement could overcome. The mathematics were unforgiving. As aircraft speeds approached the transonic region, propeller efficiency collapsed catastrophically. Propeller tips, moving at the sum of the aircraft's forward speed and their own rotational velocity, would begin to encounter compressibility effects that destroyed their ability to generate thrust efficiently. Beyond a certain speed, roughly 400 to 450 miles per hour at sea level, adding more engine power to a propeller-driven aircraft actually decreased overall performance. The British had encountered this wall during high-speed tests of their latest Spitfire variants. Pilots reported that at maximum speed, the aircraft felt as though it were flying through thick syrup, the controls becoming mushy and unresponsive, the engine screaming at maximum power but producing no additional velocity. German pilots, pushing their Messerschmitt fighters to similar speeds, reported identical phenomena. But where German engineers saw a temporary limitation to be overcome through incremental improvements, Allied engineers saw a fundamental barrier that required revolutionary solutions. The difference in perception would prove decisive. Germany would spend the next several years attempting to extract additional performance from essentially conventional designs. The Allies would spend the same period developing entirely new forms of propulsion. Decision to fully commit to jet propulsion was made in a series of meetings at the British Air Ministry during the winter of 1941. The participants included some of the most distinguished names in British aviation: Geoffrey de Havilland, Ernest Hives from Rolls-Royce, and Frank Whittle himself, still dirty from another day of engine testing. The conversation was technical, focused on production schedules and metallurgical constraints rather than strategic vision or technological dreams. The central question was not whether jet engines could work. Whittle had already proven that. The question was whether they could be made to work reliably enough and in sufficient quantities to affect the outcome of the war. The answer required a level of industrial commitment that went far beyond anything previously attempted in aviation manufacturing. Rolls-Royce, the firm that had built the Merlin engines powering Britain's Spitfires and Hurricanes, agreed to take on the challenge of mass-producing jet engines. But they insisted on design modifications that prioritized manufacturability over peak performance. Turbine inlet temperatures would be kept conservative to preserve blade life. Material specifications would emphasize availability over theoretical superiority. Manufacturing tolerances would be relaxed wherever possible to speed production and reduce rejection rates. To German engineers, obsessed with technical perfection, such compromises would have seemed like surrender. To British engineers, facing the prospect of industrial warfare against the combined might of Nazi Germany, they represented the difference between building a few perfect engines and building enough adequate engines to win a war. The commitment was formalized in a series of production orders that dwarfed anything previously seen in aviation manufacturing. Where previous aircraft programs had been measured in hundreds of units, jet engine production was planned in thousands. Where previous engines had been built by small teams of specialists, jet engines would be manufactured on assembly lines by workers who might never have seen the inside of an aircraft factory before the war began. The transformation of British industry to support jet production was accomplished with a speed that seemed impossible even to those directing it. Factories that had manufactured textiles were retooled to produce turbine blades. Precision instrument makers found themselves manufacturing fuel injection systems. Coal mines provided the raw materials for high-temperature alloys. The entire industrial base of the nation was being reconfigured to support a technology that had existed in operational form for less than 2 years. By the end of 1941, as German armies froze outside Moscow and the United States entered the war following Pearl Harbor, the balance of jet development had shifted fundamentally. Germany still possessed more advanced individual engines and more operational experience jet aircraft, but Britain had achieved something far more significant. They had created an industrial system capable of turning jet engines from unique prototypes into mass-produced weapons of war. The irony was perfect, though it would not become apparent for several more years. Germany had invented the jet age through brilliance and daring. Britain was about to win it through discipline and manufacturing capacity. The laughter in Goering's office had been premature, but it would continue for some time yet. The mathematics of industrial production moved slowly, and the ledger of aerial warfare would take years to balance. But when it did, the numbers would tell a story that no amount of individual genius or technological sophistication could overcome. The age of wonder weapons was ending before it had properly begun. The age of industrial warfare was about to demonstrate, with brutal mathematical precision, that quantity possessed a quality all its own. And in the factories of Britain and soon America, that lesson was being written in steel and fire, one engine at a time. The industrial transformation that began in British factories during the winter of 1941 represented more than a shift in manufacturing priorities. It marked the moment when the improvisational genius of wartime innovation gave way to the methodical brutality of mass production. While German engineers continued to pursue technological perfection in increasingly elaborate designs, their Allied counterparts were learning to breathe fire on an industrial scale. The Rolls-Royce factory at Barnoldswick became the epicenter of this transformation. Built originally to manufacture textiles, the facility had been hastily converted for aircraft engine production as Britain mobilized for total war. But the arrival of jet engine manufacturing demanded changes that went far beyond anything previously attempted in aviation. The very air inside the factory had to be purified to prevent contamination of turbine blade surfaces. The concrete floors were reinforced to handle machinery that operated under stresses no peacetime factory had ever encountered. Most dramatically, entirely new categories of industrial workers had to be trained to handle materials and processes that existed nowhere else in British manufacturing. The morning shift at Barnoldswick began each day at precisely 6 o'clock, with the sound of steam hammers shaping turbine discs from billets of high-temperature steel. The noise was extraordinary, a thunderous percussion that could be heard for miles across the Yorkshire countryside. Workers arriving for their shifts would find their lunch boxes vibrating on the factory benches from the reverberations of machinery that operated at temperatures hot enough to melt copper. Mary Thornton, a former textile worker who found herself assigned to turbine blade inspection, later described the sensory assault of the factory floor in letters to her sister. "You cannot imagine the heat, Eleanor. Even in December, with snow falling outside, the air near the furnaces shimmers like summer pavement. The blades come out glowing orange, and we must wait for them to cool before we can handle them with special tongs. The noise never stops. Hammering, grinding, the roar of gas flames hot enough to cut steel. By the end of each shift, my clothes are soaked with perspiration, and my ears ring for hours. But the most remarkable aspect of the transformation was not the physical demands it placed on workers, but the precision it demanded from an industrial system that had never before attempted to manufacture anything approaching this level of complexity. Jet engines required tolerances measured in thousandths of inches, maintained across thousands of individual components, assembled by workers who had learned their skills on the job during the most desperate period of British history. The engineering drawings that guided this process told a story of systematic compromise between theoretical perfection and practical manufacturability. Where German designs specified exotic alloys available only in small quantities, British drawings called for steel grades that could be produced in tonnage lots. Where German engines demanded hand fitting by master craftsmen, British designs incorporated adjustable assemblies that could accommodate normal manufacturing variations. The centrifugal compressor that formed the heart of British jet engines was, by the standards of advanced aerodynamics, a crude device. Its pressure ratio was lower than what axial designs could achieve in theory. Its frontal area was larger, creating more drag when installed in aircraft. But it possessed one overwhelming advantage. It could be manufactured by workers with limited experience, using tools and techniques adapted from existing industrial processes. The compressor wheels themselves were machined from solid billets of steel, using modified lathe equipment originally designed locomotive components. The process was laborious, requiring multiple cutting operations and frequent tool changes, but it was reproducible and scalable. Where German axial compressors demanded precision casting techniques that existed only in a handful of specialized facilities, British centrifugal compressors could be manufactured anywhere with adequate machine tools and electrical power. The combustion chambers presented different challenges but received similar solutions. Early German designs had achieved high efficiency through complex geometries that maximized fuel mixing and heat transfer. British designs sacrificed theoretical efficiency for manufacturing simplicity, using welded steel constructions that could be assembled by skilled shipyard workers, using techniques adapted from boiler manufacturing. The result was engines that performed modestly but ran reliably. Where German jet engines achieved impressive thrust-to-weight ratios through advanced materials and precise manufacturing, British engines achieved adequate performance through conservative design and robust construction. The difference would prove decisive when measured across thousands of engines rather than individual prototypes. By the spring of 1942, British jet engine production had reached a rhythm that would have seemed impossible just months earlier. The Rolls-Royce factory was completing 3 engines per week, each one representing several tons of strategic materials and hundreds of hours of skilled labour. More significantly, the production rate was accelerating as workers gained experience and manufacturing processes were refined. The statistical ledgers that tracked this progress told a story of industrial warfare in its purest form. Engine number 1 had required 2,847 man-hours to complete. Engine number 50 required 1,923 man-hours. Engine number 100 required 1,456 man-hours. The learning curve was steep and consistent, driven by the accumulated experience of workers who were literally inventing mass production techniques for technologies that had never before existed outside of research laboratories. Quality control presented challenges that required entirely new approaches to manufacturing inspection. Traditional aircraft engines could be tested by starting them and listening for irregular sounds, or feeling for unusual vibrations. Jet engines operated at temperatures and speeds that made such sensory evaluation impossible. Instead, British factories developed systematic testing protocols that measured dozens of performance parameters under controlled conditions. Every engine was subjected to a standardized test regime that began with low-speed rotation checks and progressed through increasingly demanding operational scenarios. Fuel flow rates were measured and recorded, turbine temperatures were monitored continuously, vibration signatures were analyzed for patterns that might indicate incipient failures. The process required 4 hours per engine and consumed quantities of aviation fuel that would have powered a fighter aircraft for multiple combat missions. But the investment paid dividends that became apparent only when engines reached operational squadrons. British jet engines entering service in 1942 demonstrated mean time between major maintenance intervals of 150 hours, compared to German engines of the same period that required overhaul after 25 to 50 hours of operation. The difference was not dramatic in individual terms, a factor of 3 or 4, but when multiplied across hundreds of engines, it represented the difference between sustainable operations and logistical collapse. The Americans, entering jet development as a latecomer but with industrial advantages that dwarfed even British capabilities, approached the challenge with characteristic methodology. General Electric, tasked with manufacturing jet engines based on British designs, immediately began redesigning British components for American manufacturing methods. Where British factories used skilled workers operating individual machine tools, American factories employed semi-skilled workers operating production machinery designed for high-volume output. The cultural differences were profound and sometimes led to confusion among British engineers observing American manufacturing techniques. Jack Newhouse, a Rolls-Royce engineer sent to General Electric's facility in Lynn, Massachusetts to assist with technology transfer, wrote in his diary, "The Americans manufacture engines the way Ford manufactures motor cars, as if they intended to build thousands of them. They have redesigned our fuel injection system to use standardized fittings available from industrial suppliers. They have modified our turbine blade attachment method to eliminate hand fitting entirely. Most remarkably, they have created an assembly line where engines move from station to station, with different teams performing specialized operations at each position." The American approach sacrificed the craft tradition that had characterized British engine manufacturing in favor of industrial efficiency that could scale to meet the demands of global warfare. Where British factories built engines one at a time, with individual workers responsible for major sub-assemblies from start to finish, American factories divided the process into dozens of specialized operations, each performed by workers who might handle only a single component type throughout their entire employment. The result was a manufacturing system capable of exponential expansion. By the end of 1942, American jet engine production was approaching parity with British output, despite having started nearly 2 years later. By mid-1943, American factories were producing more jet engines per month than German factories had manufactured since the beginning of their program. But the most significant advantage of Allied manufacturing was not speed or quantity, though both were impressive. It was standardization. While German jet engines remained largely handcrafted devices, with individual engines varying significantly in performance characteristics and maintenance requirements, Allied engines were designed from the beginning for interchangeability and commonality of parts. A turbine blade manufactured at Rolls-Royce could be installed in an engine assembled at General Electric. Fuel injection systems were standardized across different engine variants. Most critically, maintenance procedures and spare parts requirements were identical regardless of where individual engines had been manufactured. The implications for sustained military operations were profound. German mechanics working on Me-262 jet fighters were often forced to cannibalize parts from other aircraft to keep individual machines operational. Allied mechanics had access to standardized spare parts, manufactured in quantities sufficient to support extended operations. German pilots learned to nurse their engines through each mission, carefully managing fuel flow and operating temperatures to maximize service life. Allied pilots could operate their engines at full power with confidence that replacement engines would be available when overhauls became necessary. The mathematical progression was relentless and ultimately decisive. German jet engine production peaked in late 1944 at approximately 50 engines per month, representing the absolute maximum output achievable by an industrial system optimized for quality over quantity. Allied production during the same period exceeded 300 engines per month and was still accelerating. More critically, Allied engines entering service were demonstrating operational lifespans 3 to 5 times longer than their German counterparts. The ledger of aerial warfare was beginning to balance, and the numbers told a story that no amount of individual technical superiority could overcome. Germany had built faster engines, more sophisticated engines, engines that represented the absolute pinnacle of contemporary engineering achievement. But the Allies had built more engines, more reliable engines, engines that could be manufactured, maintained, and replaced at a rate sufficient to sustain industrial warfare. The transformation of Allied manufacturing during this period represented one of the most remarkable technological achievements in human history. In less than 3 years, industrial facilities designed for peacetime production had been reconfigured to manufacture technologies that had existed only in prototype form when the war began. Workers with no previous experience in advanced engineering had learned to produce components requiring precision measured in thousandths of inches. Management systems had evolved to coordinate production across multiple facilities and 2 continents. But perhaps most significantly, the Allied approach to jet engine manufacturing had established principles that would govern industrial development for decades to come. The emphasis on standardization over customization, on reproducibility over individual craftsmanship, on systematic process improvement over inspired innovation, would become the foundation of post-war industrial growth. The Germans, brilliant in their individual achievements, but constrained by an industrial philosophy that prioritized perfection over scalability, had created technological marvels that could not be sustained under the pressures of total war. The Allies, methodical in their approach but unlimited in their industrial capacity, had created technologies that were adequate rather than exceptional, but could be produced in quantities sufficient to overwhelm any opposition. As 1943 dawned, the industrial transformation was complete. The question was no longer whether jet engines could work, or even whether they could be manufactured in quantity. The question was whether German technology, no matter how advanced, could compete with Allied manufacturing capacity. Answer was becoming increasingly clear, written in the production statistics that flowed from factories across Britain and America like an industrial avalanche that would eventually bury the Reich beneath its own mathematical inevitability. The ledgers told the story with mathematical precision. By the winter of 1943, the numbers flowing from Allied production facilities had begun to assume a momentum that transcended mere manufacturing efficiency. They represented the transformation of industrial capacity into strategic dominance, the moment when quantity began to assert a quality that no amount of individual technological superiority could overcome. At the Rolls-Royce facility in Barnoldswick, the monthly production meetings had taken on an almost ritualistic character. Engineers and production managers gathered around tables covered with statistical charts that tracked every measurable aspect of jet engine manufacturing. Output per worker hour, mean time between failures, materials, consumption per unit produced, rejection rates at final inspection. Each number told part of a larger story that was reshaping the fundamental nature of aerial warfare. Plant manager Harold Morrison, a soft-spoken man who had spent 30 years in textile manufacturing before finding himself responsible for the most advanced propulsion technology in human history, opened each meeting with the same question. What did we learn this month that we didn't know last month? The answers revealed an industrial system that was evolving with startling speed. October 1943. Workers had discovered that turbine blades, rejected for minor surface imperfections, could be reconditioned using hand polishing techniques adapted from watchmaking. Result? Material waste reduced by 12%, production rate increased by 8%. November 1943. A modification to fuel injection nozzle geometry, suggested by a shop floor mechanic who had previously worked on diesel engines, improved combustion efficiency by 6% while reducing manufacturing complexity. Result? Fuel consumption per engine reduced. Manufacturing time per unit decreased by 45 minutes. December 1943. Implementation of statistical quality control methods borrowed from munitions manufacturing allowed earlier detection of manufacturing variations that could lead to field failures. Result? Engine reliability increased by 23%. Field maintenance requirements reduced by nearly 1/3. These incremental improvements, individually modest, accumulated into advantages that fundamentally altered the strategic balance. An Allied jet engine that entered service in late 1943 was not merely manufactured more quickly than its early war predecessors, it was more reliable, more fuel efficient, and easier to maintain. Most critically, it was one of hundreds being produced each month rather than one of dozens. The contrast with German production became starker with each passing month. While Allied factories refined their processes through systematic improvement, German facilities struggled with increasingly desperate resource constraints. The exotic alloys that enabled superior performance in German engines were becoming unavailable as Allied bombing disrupted supply chains and strategic materials were diverted to other priorities. Skilled craftsmen who had hand-fitted engine components were being conscripted for infantry service as manpower shortages reached crisis levels. Oberingenieur Klaus Richter, responsible for quality control at the Junkers engine facility in Dessau, documented the deterioration in monthly reports that read like medical records of a dying industrial system. January 1944. Deliveries of Krupp steel delayed by transportation difficulties. 17 engines completed this month using inferior substitute alloys. Estimated service life reduced to approximately 30 hours. March 1944. Critical shortage of experienced machinists. New workers require extensive training but demonstrate acceptable competency after 6 to 8 weeks. Production rate temporarily reduced. May 1944. Allied bombing of rail infrastructure has created severe delays in component delivery. Recommends stockpiling critical materials to maintain production continuity. But stockpiling was a luxury the German war economy could no longer afford. Raw materials were being allocated according to immediate military priorities, and jet engines, for all their technological sophistication, represented a relatively small portion of total aircraft production. The Messerschmitt Me-262, which would eventually become Germany's primary operational jet fighter, was competing for resources with the conventional aircraft that still formed the backbone of the Luftwaffe. The resource allocation decisions made during this period reveal the fundamental strategic miscalculation that would doom German jet development. Rather than concentrating limited resources on perfecting and mass-producing a single reliable jet engine design, German planners continued to pursue multiple parallel development programs, each competing for the same scarce materials and skilled personnel. Heinkel continued development of their HES 011 engine, an advanced design that promised significantly improved performance over earlier models. Junkers pursued their UMO 004 series, optimizing for manufacturability rather than peak performance. BMW worked on their 003 engine, incorporating innovative features that might provide decisive advantages. Each program represented enormous investments of time, materials, and expertise. Together, they ensured that no single design received sufficient resources to achieve true mass production. The Allied approach was methodical to the point of appearing pedestrian by comparison. Having identified a jet engine design that achieved adequate performance with acceptable reliability, British and American manufacturers focused their efforts on systematic improvement of manufacturing processes rather than revolutionary advances in engine technology. The result was a production system that generated incremental improvements continuously while maintaining output rates that dwarfed German capabilities. General Electric's facility in Lynn, Massachusetts, had become a shrine to this philosophy of systematic improvement. The factory floor was organized with mathematical precision, each workstation positioned to minimize the time required to move components between manufacturing operations. Workers followed standardized procedures that had been refined through months of careful observation and measurement. Quality control inspections were performed at predetermined intervals using gauges and fixtures that ensured consistent results regardless of individual inspector experience. The transformation of American workers into precision manufacturers of jet engines represented one of the most remarkable educational achievements of the war. Men and women who had spent their careers in textile mills, automobile factories, and agricultural equipment manufacturing were producing components that required tolerances measured in thousands of inches. The training programs developed to accomplish this transformation would become models for industrial education throughout the post-war period. Dorothy Martinez, a former seamstress who found herself inspecting turbine blades at the General Electric facility, later described the psychological adjustment required. In textiles, if a seam was slightly crooked, you could adjust it or work around it. With turbine blades, everything had to be perfect. We learned to use measuring instruments more precise than anything I had ever seen. A variation of 0.003 of an inch in blade angle could cause the entire engine to fail catastrophically. The responsibility was enormous, but we understood that pilots' lives depended on our precision. The statistical evidence of this precision was accumulating in maintenance logs and operational reports from Allied squadrons beginning to receive jet-powered aircraft. The Gloucester Meteor, Britain's first operational jet fighter, was demonstrating reliability levels that exceeded even optimistic projections. Engine overhaul intervals were averaging 175 hours of operation, compared to German jets that required major maintenance after 25 to 50 hours. More significantly, Allied jet engines were proving capable of sustained high-power operation without the careful throttle management that German pilots had learned was essential for engine survival. Flight Lieutenant James Patterson, among the first RAF pilots to fly jet aircraft operationally, recorded his impressions in letters home that capture the technological revolution taking place. "Flying a jet is like nothing you can imagine, Mother. There is no vibration from a propeller, no complex mixture controls to manage, no torque effects to compensate for during takeoff. You advance the throttle and the aircraft simply accelerates with smooth, steady power. The silence is extraordinary. All you hear is the rush of wind and a distant whistle from the engine. But most remarkable is the reliability. These engines start every time, run smoothly through all power settings, and require virtually no attention from the pilot during flight. The contrast with German pilot experiences was stark. Luftwaffe jet pilots were learning to treat their engines like delicate instruments, requiring constant attention and careful management. Engine starting procedures required precise timing and could fail if ambient temperatures were too low or too high. Fuel management demanded continuous monitoring to prevent combustion chamber temperatures from exceeding safe limits. Most critically, German jet engines were prone to sudden, catastrophic failures that could destroy an aircraft with no warning. Hauptmann Werner Nowotny, one of Germany's most experienced jet pilots, described the psychological stress of flying aircraft powered by unreliable engines. Every mission is a gamble, not just with enemy fighters, but with your own power plant. The engines run hot, and you never know when the turbine might disintegrate without warning. We have learned to listen constantly for changes in engine note that might indicate impending failure. Many good pilots have been lost not to enemy action, but to engine failures during critical phases of flight. But the most damning evidence of German industrial failure was emerging from maintenance facilities attempting to keep German jet fighters operational. Spare parts were becoming increasingly difficult to obtain as production facilities struggled with material shortages and transportation disruptions. Engine overhauls required components that were often unavailable, forcing mechanics to cannibalize parts from other aircraft or attempt field repairs using improvised materials. Feldwebel Heinrich Müller, a senior mechanic with Jagdgeschwader 7, one of the Luftwaffe's primary jet fighter units, kept detailed logs of maintenance activities that document the progressive deterioration of German logistics. Engine number 280442 removed after 23 hours due to turbine blade failure. No replacement engine available. Attempted repair using blades salvaged from engine 280391. Repair completed after 72 hours, but engine performance reduced approximately 15%. Aircraft returned to operational status, but restricted to emergency missions only. These maintenance challenges were compounded by the increasing tempo of Allied bombing attacks on German industrial facilities. The carefully orchestrated production networks that had enabled German technical achievements were being systematically destroyed by Allied air power. Component suppliers were disrupted, transportation networks were severed, and skilled workers were either killed in bombing raids or diverted to air defense duties. The irony was perfect and devastating. German jet aircraft, when operational, remained superior to Allied jets in many performance categories. The Me-262 was faster than the Gloster Meteor. German jet engines achieved higher thrust-to-weight ratios than Allied designs. German pilots, when flying functional aircraft, could outperform Allied pilots in individual engagements. But operational readiness rates for German jet units rarely exceeded 30%, compared to Allied units that maintained 70 to 80% readiness. The mathematics of sustained operations were unforgiving. A German jet unit with 12 aircraft might have 4 available for missions on any given day. An Allied unit with the same number of aircraft would typically have 9 or 10 ready for combat. Over time, this difference in availability translated into overwhelming Allied superiority in actual combat operations, regardless of individual aircraft performance. The production statistics for late 1943 tell the story with brutal clarity. German factories, operating under increasingly desperate conditions, managed to produce approximately 180 jet engines between October and December 1943. Allied factories during the same period produced over 850 jet engines, with production rates still accelerating. More critically, Allied engines entering service were demonstrating operational lifespans 4 to 6 times longer than German engines, meaning that each Allied engine represented substantially more actual combat capability than its German counterpart. By early 1944, the accumulated weight of these production advantages was beginning to manifest in combat operations. Allied jet aircraft were appearing in increasing numbers over European battlefields, while German jet units struggled to maintain minimum operational strength. The technological advantage that Germany had held through superior individual engineering was being systematically overwhelmed by Allied industrial capacity. The ledger of aerial warfare was approaching its final reconciliation, and the numbers told a story that no amount of individual genius or technological sophistication could overcome. Germany had created magnificent engines that represented the pinnacle of contemporary engineering achievement. But the Allies had created adequate engines in sufficient quantities to dominate the skies through sheer weight of numbers. The age of wonder weapons was ending, and the age of industrial warfare was about to render its final verdict. The panic began with statistics. In the spring of 1944, as Allied forces prepared for the invasion of Normandy and German defences crumbled across multiple fronts, the numbers flowing into Reichsmarschall Hermann Göring's headquarters told a story of technological triumph transformed into strategic catastrophe. The same man who had dismissed jet engines as toys for professors now found himself confronting production reports that revealed the mathematical inevitability of German defeat. The contrast was so stark it seemed impossible. Allied jet engine production for the first quarter of 1944 had reached 1,247 units. German production for the same period totaled 156 engines. But the raw numbers, devastating as they were, told only part of the story. Allied engines entering service were demonstrating mean operational lifespans of 180 hours. German engines, built from increasingly inferior materials by workers with minimal training, were failing after an average of 18 hours of operation. The mathematics were simple and unforgiving. Each Allied engine represented 10 times the operational capability of its German counterpart. Multiplied across thousands of engines, this disparity created an insurmountable advantage that no amount of tactical brilliance or individual technical superiority could overcome. Germany was losing the jet age through the same methodical process that was destroying its conventional forces, the grinding arithmetic of industrial warfare. Oberst Adolf Galland, one of Germany's most experienced fighter pilots and a vocal advocate for jet development, attempted to quantify the crisis in a memo that reached Hitler's desk in April 1944. Mein Führer, we face a fundamental problem of industrial mathematics. Our jet engines are superior in individual performance, but they cannot be produced in sufficient quantities or operated for sufficient duration to affect the outcome of air operations. We are building racing cars when we need trucks. The comparison was apt, though Galland could not have known how precisely it captured the strategic reality. German jet engines were indeed racing cars, sophisticated, high-performance machines that demanded expert maintenance and operated at the limits of their capabilities. Allied jet engines were trucks, reliable, maintainable devices designed for sustained operation under adverse conditions. In peacetime, the German approach might have been superior. In total war, it was catastrophic. Production facilities that had once been sources of German pride were becoming monuments to strategic miscalculation. The Junkers factory in Dessau, which had achieved remarkable technical breakthroughs in jet engine design, was struggling to maintain production of 50 engines per month, while Allied facilities were completing 50 engines per week. More critically, the German engines emerging from Dessau required twice as many man-hours to manufacture as Allied engines, and demonstrated half the operational lifespan. Plant manager Karl Friedrichs, in his final report before the facility was overrun by advancing Soviet forces, provided a clinical assessment of industrial failure. The fundamental problem is not technical competence but resource allocation. We continue to pursue perfection when adequacy would serve our purposes better. Each engine requires 340 hours of skilled labour to complete, compared to British engines that require approximately 120 hours. Our engines achieve superior performance specifications, but cannot be produced in quantities sufficient to meet military requirements. The resource allocation decisions that had seemed prudent in 1941 were revealing their catastrophic consequences by 1944. Germany had invested enormous resources in developing multiple competing jet engine designs, each representing different approaches to the same fundamental challenge. The Junkers UMO 004 prioritised manufacturability. The Heinkel HES 011 pursued maximum performance. The BMW 003 incorporated innovative design features. Together, they consumed resources that might have enabled mass production of a single standardized design. The Allied approach, methodical and apparently unimaginative by comparison, was demonstrating the overwhelming advantages of industrial focus. Rather than pursuing multiple, parallel development programs, British and American manufacturers had concentrated their efforts on perfecting the production of engines that achieved adequate performance with exceptional reliability. The result was a manufacturing system capable of exponential expansion that German industry, for all its technical sophistication, could never match. The human cost of German strategic miscalculation was becoming apparent in pilot training programs that could no longer provide adequate preparation for jet operations. Flight training required operational aircraft, but operational aircraft were increasingly unavailable due to maintenance difficulties and parts shortages. German jet pilots were entering combat with fewer flight hours than their propeller-driven predecessors, flying aircraft that were more complex and less reliable than any previous fighter. Lieutenant Hans Müller, assigned to Jagdgeschwader 7 in March 1944, recorded his training experience in a diary that survived the war. We received 12 days of ground instruction on jet engine operation, followed by 4 flights in aircraft borrowed from operational squadrons. The engines are temperamental beyond belief. They must be started according to precise procedures, warmed up gradually, and operated within narrow temperature limits. Any deviation from proper procedure can result in catastrophic failure. We are expected to master in weeks what should require months of training. The operational consequences were predictable and tragic. German jet units, when they could achieve operational status, demonstrated loss rates that exceeded even the desperate days of 1943. Aircraft were being destroyed not primarily through enemy action, but through mechanical failures, pilot errors arising from inadequate training, and maintenance difficulties that left aircraft grounded for weeks at critical moments. The contrast with Allied operations was stark and demoralizing. RAF and USAAF pilots transitioning to jet aircraft received extensive training on reliable aircraft that started consistently, operated predictably, and failed gracefully when maintenance was required. Allied jet units were achieving operational readiness rates that exceeded conventional squadrons, while German units struggled to maintain minimum strength. Squadron leader Michael Henderson, commanding one of the first operational RAF jet units, describes the transformation in operational capability. Jet aircraft have simplified many aspects of fighter operations. Engine management is straightforward. You advance the throttle and the aircraft accelerates smoothly without the complex power management required by piston engines. Maintenance is more predictable because engine operating parameters are consistent between aircraft. Most significantly, engine reliability has eliminated many of the emergency situations that plagued conventional operations. But the most devastating aspect of German failure was not technical but strategic. The jet engine technology that Germany had pioneered was being used more effectively by their enemies than by German forces themselves. Allied jet aircraft were beginning to appear in significant numbers over German territory, while German jet units remained largely experimental forces with minimal impact on overall air operations. The production statistics for mid-1944 revealed the full extent of the transformation. Allied factories were completing approximately 400 jet engines per month, with production rates still accelerating as manufacturing techniques were refined and expanded. German production had plateaued at fewer than 80 engines per month and was declining as resource shortages and bombing disrupted manufacturing facilities. More critically, the operational lifespan disparity was widening rather than narrowing. Allied engines entering service in 1944 were demonstrating mean operational lives exceeding 200 hours, while German engines were failing after fewer than 20 hours of operation. The cumulative effect was overwhelming. Each month of operations increased Allied numerical superiority, while German forces struggled to maintain minimum operational capability. The mathematical progression was relentless and ultimately decisive. By late 1944, Allied forces possessed more operational jet aircraft than Germany had produced during the entire war. Allied pilots were accumulating flight experience on reliable aircraft, while German pilots were grounded by maintenance difficulties. Allied maintenance crews had access to standardized spare parts manufactured in quantity, while German mechanics resorted to increasingly desperate improvisation. The strategic implications extended far beyond individual air operations. Germany's failure to achieve sustainable jet production meant that the technological advantage they had pioneered was being systematically exploited by their enemies. The same jet technology that might have provided decisive tactical advantages was instead accelerating German defeat through the superior industrial capacity of Allied nations. The irony was perfect, devastating, and historically decisive. Germany had invented the future of aviation through individual brilliance and technical innovation. But they had failed to industrialize that future through the systematic application of manufacturing capacity and organizational discipline. The Allies, methodical rather than brilliant, had transformed German innovations into weapons of German destruction. Hermann Goering's laughter had finally stopped. In its place was the grinding sound of Allied production lines operating 24 hours per day, turning out the engines that would power the final assault on the Reich. The ledger of aerial warfare was approaching its final balance, and the numbers told a story of mathematical inevitability that no amount of individual genius could overcome. The age of wonder weapons was ending in the rubble of German cities bombed by aircraft powered by German innovations manufactured in Allied factories. The verdict of total war was being written in production statistics, maintenance, logs and operational readiness reports that documented the transformation of technological superiority into strategic catastrophe. The future belonged not to those who could invent it, but to those who could build it in sufficient quantities to reshape the world.